What does it take to build a plane that flies faster than a speeding bullet, higher than most missiles can reach, and remains nearly invisible to radar? At the height of the Cold War, a small team of brilliant engineers took on a challenge that seemed straight out of science fiction and made it a reality. The Lockheed A-12, a spy plane like no other, wasn't just fast, it was a triumph of human ingenuity, born from the highly classified Project OXCART. This aircraft pushed the boundaries of 1960 technology to the breaking point. But how did they do it? What secrets lie behind its titanium skin and revolutionary design? In this video, we're pulling back the curtain on the insane engineering that made the A-12 a plane and a legend. Buckle up as we explore the innovations, challenges, and sheer audacity behind one of history's most ambitious aerospace projects. The birth of Project OXCART. In the late 1950s, the Central Intelligence Agency recognized the growing limitations of the Romanist spy plane program. The Soviet Union's defense systems accurately tracked the menace to flights from their very first mission, signaling an urgent need for a more advanced reconnaissance aircraft. The U-2's vulnerability became starkly apparent when Francis Gary Powers' aircraft was shut down over Soviet territory in May 1960. Consequently, the CIA initiated efforts to develop a successor aircraft that could operate beyond the reach of Soviet air defenses. Initial attempts to reduce the U-2's radar cross-section through Project Rainbow proved unsuccessful, prompting the search for an entirely new approach. Under Project Gusto, the CIA solicited design proposals from both Lockheed and Convair. Notably, while Convair's KINGFISH design featured superior radar evading characteristics, Lockheed's proposal offered better performance specifications and significantly lower projected costs. The CIA's final decision favored Lockheed, specifically considering their track record with the MINIST program, which had been delivered on schedule and under budget. In contrast, Convair's MINIS-58 program had experienced numerous delays and cost overruns. Clarence Kelly Johnson, leading Lockheed's Skunk Works, approached the challenge methodically. The aircraft specifications were unprecedented. It needed to fly at Mach 3 to reach altitudes of 91,000 feet while maintaining the smallest feasible radar cross-section. Johnson's team developed 12 different design concepts, designated as Archangel Menace 1 through Archangel Menace 12, before reaching the final configuration. The initial Menace 1 design featured a conventional fuselage spanning 166.67 feet, an empty weight of 41,000 pounds, fuel capacity of 61,000 pounds, target cruise speed of Mach 3.0. The development process proved exceptionally challenging. Johnson noted in his log that they were having a horrible time building the first airplane. Furthermore, the project's complexity led to significant cost escalations, reaching $136 million by October 1961. The CIA, recognizing these challenges, assigned a senior aeronautical engineer to monitor the program at Lockheed's facility. On January 26, 1960, the CIA officially ordered 12 MINIS-12 aircraft. The program demanded unprecedented innovations in multiple domains, including titanium fabrication, specialized lubricants, advanced jet engines, and sophisticated pilot life support systems. This comprehensive engineering effort essentially created its industrial base, requiring approximately 2,400 skilled workers for manufacturing and fabrication. Breaking material science barriers, manufacturing innovation stood at the heart of the A-12 OXCART's development, with titanium emerging as the cornerstone material for this groundbreaking aircraft. The A-12's construction demanded unprecedented solutions in metallurgy and materials science. The A-12's airframe required a material capable of withstanding temperatures between 500 and 600 degrees Fahrenheit, with some areas near the engines reaching beyond 1,000 degrees. Initially, 93% of the A-12 structure consisted of titanium alloy. Rather ironically, the CIA orchestrated a covert operation to acquire titanium from the Soviet Union, using third-world countries and dummy companies as intermediaries. One particularly clever ruse involved creating bogus operations, claiming to need titanium for pizza ovens. The development of new manufacturing techniques was fraught with significant challenges. Early on, nearly 95% of the titanium material delivered failed to meet quality control standards. The Skunk Works team faced numerous obstacles, including titanium's extreme hardness, which quickly destroyed conventional machining tools, and the contamination of welded joints caused by chlorinated tap water. Standard manufacturing protocols and traditional aerospace assembly techniques proved ineffective for this groundbreaking project. An unexpected issue arose when titanium panels welded during the summer months began failing within 6 weeks, a problem traced back to the heavily chlorinated water supply in Burbank. The breakthrough came with the introduction of distilled water in the manufacturing process, allowing the team to overcome these hurdles and push forward with production. The A-12's design incorporated pioneering composite materials, particularly in radar-absorbing sections. The aircraft's distinctive chains featured an innovative combination of iron, ferrite, and silicon laminate, bonded with asbestos for enhanced radar absorption. These composites proved crucial for maintaining the aircraft's low radar cross-section, altogether with its structural integrity. The engineering team developed specialized materials for different sections of the aircraft. The outward-pointing teeth of the aircraft structure utilized titanium, whereas the inward-pointing sections incorporated radar-absorbent composites. This strategic material placement enhanced both the aircraft's structural strength and its stealth capabilities. The development process required creating entirely new synthetic lubricants that remained functional at extreme temperatures. These lubricants exhibited unique properties, appearing almost solid at room temperature. The team also formulated specialized hydraulic fluids capable of maintaining performance from subsonic to supersonic speeds, pushing propulsion boundaries. The J-58 engine originated from a 1956 Navy aviation project, subsequently becoming the most powerful air-breathing propulsion system ever created at that time. Each J-58 generated an astounding 160,000 horsepower, equivalent to 32,000 pounds of thrust. The engine's development faced extraordinary metallurgical challenges as operating conditions pushed beyond conventional limits. Maximum fuel temperatures reached 700 degrees Fahrenheit, engine inlet temperatures exceeded 800 degrees, and turbine inlets operated above 2,000 degrees Fahrenheit. The air inlet system incorporated a revolutionary, spike-shaped cone protruding from the engine inlets. These spikes regulated incoming airflow by decelerating, compressing, and superheating it before entering the bypass engines. Without this innovative spike system, the J-58 engines would have produced merely 20% of the power required by the A-12. The inlet control system presented formidable engineering challenges. The primary issue involved mechanical controls that failed to respond quickly enough to shockwave variations, resulting in engine unstarts that caused violent buffeting. Accordingly, engineers developed an electronic control system and ultimately redesigned the inlet configuration, allowing the spike to move up to 26 inches at supersonic speeds. The A-12's fuel system required entirely new solutions for high-temperature operations. The aircraft's fuel tanks, holding approximately 11,000 gallons, experienced temperatures reaching 350 degrees Fahrenheit. This extreme environment necessitated the development of J-7, a specialized fuel with low vapor pressure and high flash point so stable that conventional ignition methods proved ineffective. The engineering team grappled with ongoing difficulties in finding suitable fuel tank sealants. They needed a material capable of resisting the chemical effects of the fuel, maintaining elasticity despite extreme temperature fluctuations. and enduring significant pressure changes, yet no existing solution met all these demands. Subsequently, this limitation led to persistent fuel leaks, discovered only after the first aircraft's delivery to the test site. The fuel system incorporated heat exchangers and smart valves, enabling the fuel to serve as an internal coolant. Moreover, the engine startup process required triethylborane, a chemical that ignited spontaneously upon contact with air. Thermal management innovation. Managing extreme temperatures posed one of the most formidable challenges in the A-12 OXCART's development. The aircraft's skin endured temperatures between 500 and 600 degrees Fahrenheit across most surfaces, creating unprecedented thermal management demands. The first thing to remember, air friction at Mach 3+ speeds generates intense kinetic heating. The aircraft's external surfaces reached 800 degrees Fahrenheit. Under those circumstances, conventional aerospace materials would fail. The cockpit environment proved equally challenging, with temperatures climbing to 500 degrees Fahrenheit. The thermal loads affected both structural integrity and operational capabilities. The engineering team developed multiple innovative approaches to manage heat. The A-12's dark blue paint enabled the titanium skin to radiate heat 5 times faster than unpainted surfaces. Important to realize that this seemingly simple solution played a crucial role in thermal management. The cooling system was designed with a combination of strategically placed heat exchangers, advanced valves for precise temperature regulation, and integration with the fuel system to manage internal cooling effectively. The engineering team conducted extensive thermal load testing. The Flight Research Center executed complex evaluations combining flight and ground facility techniques. These tests generated comprehensive data about aerodynamic and thermal forces, establishing methods for separating these effects, knowledge that continues supporting modern aircraft design. The extreme operating conditions demanded entirely new hydraulic solutions. Standard aerospace fluids would vaporize at high speeds, yet needed to maintain functionality at lower altitudes. The engineering team developed synthetic lubricants with unique properties. They appeared nearly solid at room temperature and required pre-flight heating. The hydraulic system encountered numerous thermal challenges, including heat generated by flow restrictions, hot spots caused by internal leakage, and high-pressure zones that developed within the gas-filled accumulators. To maintain optimal performance, the engineering team established strict temperature controls. The hydraulic oil temperature needed careful regulation between 120 degrees Fahrenheit and 150 degrees Fahrenheit to prevent oxidation and viscosity changes. Beyond these limits, the oil would break down, producing corrosive acids and sludge that threatened system integrity. The thermal management solutions developed for the A-12 OXCART established new benchmarks in aerospace engineering. These innovations laid the groundwork for future high-speed aircraft design, demonstrating effective approaches to extreme temperature control in supersonic flight. Radar evading engineering. The A-12 OXCART pioneered radar evading technology, marking the beginning of modern stealth aircraft design. With the failure of Project Rainbow to reduce the U-2's radar detectability, Lockheed's engineers embarked on an ambitious path to create the first purpose-built stealth aircraft. The initial radar cross-section reduction efforts focused on the aircraft's shape and materials. Primarily, Edward Purcell and Franklin Rogers developed a theory that continuously curving airframes would scatter radar pulses away from their source. This concept proved fundamental to the A-12's design philosophy. The engineering team integrated several innovative features, including vertical stabilizers canted inward at a 15-degree angle, the use of non-metallic materials in critical areas, a radar-absorbing outer skin, and curved surfaces designed to deflect radar energy. Indeed, one of the most innovative developments involved a cesium-based fuel additive that created an ionizing cloud behind the aircraft. effectively concealing its rear aspect from radar waves. The A-12's distinctive, cobra-like appearance emerged from electromagnetic theory applications. Kelly-Johnson added 10 curved extensions to the engine housings and leading edges of the wings, creating the characteristic chines. Although initially concerned about aerodynamic implications, wind tunnel tests revealed that these chines enhanced the aircraft's lift capabilities. The engineering team faced a significant challenge with titanium's brittleness, which complicated the creation of curved surfaces. Hence, they developed a solution using triangular-shaped pieces called fillets attached to the framework with specially formulated epoxy resin. These components ultimately became crucial elements in the aircraft's radar evading capability. The evolution of composite materials played a vital role in advancing the A-12's stealth capabilities. Generally, the engineering team replaced metallic fillets with electrically resistive honeycomb plastic featuring a glass fiber surface. These materials demonstrated remarkable radar-absorbing properties while maintaining structural integrity at high speeds. The composite integration strategy utilized combinations of iron, ferrite, and silicon laminates, asbestos-based materials for radar absorption, and resin-impregnated, non-metallic components. Undoubtedly, the most significant breakthrough came through the strategic placement of these materials. The outward-facing surfaces utilized titanium construction, whereas inward-pointing sections incorporated radar-absorbent composites. This dual-material approach optimized both structural strength and radar-evading capabilities. The combination of shape, materials, and innovative design resulted in an aircraft that demonstrated unprecedented stealth characteristics for its era. Nevertheless, these advancements required constant refinement, as evidenced by the ongoing testing at the Indian Springs facility in Nevada. Life support systems engineering, protecting pilots at extreme altitudes and speeds, demanded unprecedented innovations in life support technology for the A-12 OXCART program. The combination of uninsulated cockpits and operations at altitudes above 90,000 feet created survival challenges that standard aviation equipment could not address. The David Clark Company and Firewall Corporation collaborated to create this -901 pressure suit, a groundbreaking full-pressure system based on -15 rocket aircraft designs. The custom-made suits were equipped with advanced features, including thermal insulation to protect against 400-degree Fahrenheit windshield radiation, integrated cooling and pressure control systems, a self-contained oxygen supply, and comprehensive life support capabilities for high-altitude operations. Primarily, each -901 suit required precise customization, costing $30,000 in mid-1960s currency. The suits featured redundant control regulators for safety, with both primary and backup systems. Straight away, pilots discovered these suits provided their only means of survival above certain altitudes. Without them, unconsciousness would occur within 15 seconds. Thereupon, the engineering team faced unique challenges in cockpit temperature regulation. Unlike conventional aircraft, the A-12's interior remained deliberately uninsulated to reduce weight. The cockpit air conditioning underwent rigorous testing in what engineers described as a broiler big enough to roast an ox medium rare, maintaining 75 degrees Fahrenheit inside, while external temperatures reached 600 degrees. The environmental control system ensured a ventilated atmosphere with 100% oxygen breathing capability, automatic pressure regulation, and efficient temperature management to maintain pilot comfort. The emergency systems were designed with extensive safeguards for high-altitude bailouts. If ejection was required, specialized cables secured the pilot's feet to the seat during aircraft clearance, while a stabilization parachute prevented dangerous spinning during the initial descent. The sequence began with the deployment of the stabilization parachute, followed by a controlled descent of over 12 miles. At 15,000 feet, the main parachute activated, and the system automatically separated the pilot from the seat. Henceforth, the emergency oxygen system resided in the parachute backpack, ensuring survival capability independent of aircraft systems. Concurrently, the helmet design featured externally adjustable microphones and heated faceplates with tinted external visors. The pressure suit sleeves contained emergency instructions for pilots to reference during ejection procedures. Comparatively, these life support systems represented a quantum leap beyond existing aviation technology. The A-12's operational requirements, including pilot size restrictions of under 6 feet tall and 175 pounds, necessitated completely new approaches to human survival at extreme altitudes. Nonetheless, the systems proved remarkably reliable, with no recorded suit failures during operational service. Testing and validation breakthroughs. Rigorous testing and validation formed the backbone of the A-12 OXCART's development cycle. Between 1960 and 1962, extensive wind tunnel testing and flight validation programs established new benchmarks in aerospace engineering verification methods. Primarily, Lockheed engineers conducted comprehensive scale model testing at NASA's Ames Research Center, utilizing their 8-7-foot unitary plan high-speed wind tunnel. The testing program concentrated on several key areas, including the evaluation of different inlet designs, the control of cowl bleed systems, performance at Mach 3, 2, and off-design performance reaching Mach 3, 5. Following these initial tests, engineers discovered that conventional test pylons interfered with radar cross-section measurements. Ultimately, this led to a complete redesign of the testing apparatus. The validation process extended beyond aerodynamics, requiring a full-size mock-up for radar signature testing, transported hundreds of miles to specialized facilities. The first A-12, designated Article 121, underwent ground testing at Burbank in January and February 1962. The maiden flight, remarkably, almost ended in disaster. Test pilot Lou Shock encountered severe lateral oscillations, forcing a landing after less than 2 miles at just 20 feet altitude. The official first flight occurred on April 30, 1962, reaching 30,000 feet with a gross weight of 72,000 pounds. By the end of 1962, 4 additional aircraft had joined the test fleet. The program faced significant challenges between Mach 2, 4 and 2, 8, where severe turbulence threatened operational capability. The validation process employed various verification methods, including the implementation of a telemetry system. The Birdwatcher system monitored critical aircraft systems, transmitting real-time data to ground stations. Progressive performance testing began with initial flights using J-75 engines, reaching Mach 2.0, and later transitioned to J-58 engines, enabling speeds of Mach 3.2. By January 1965, the A-12 demonstrated its capabilities through a groundbreaking long-range, high-speed flight. The aircraft maintained speeds above Mach 3.1 for 75 minutes, covering 2,850 miles at altitudes between 75,600 and 80,000 feet. Through persistent refinement and testing, the A-12 achieved its design specifications of sustained Mach 3 to flight at 90,000 feet. The testing program culminated in several record-breaking achievements. In May and August 1965, the A-12 set speed and altitude records, reaching Mach 3.29 at 90,000 feet, approximately 2,500 miles per hour. These records for air-breathing piloted aircraft remain unbroken. The comprehensive testing phase concluded with 2,850 test flights, validating the A-12's position as a pioneering achievement in aeronautical engineering. Engineering legacy. Historically, the A-12 OXCART program's technological breakthroughs established foundational principles that continue shaping aerospace engineering. The program's innovations extend far beyond its operational lifespan, influencing modern aviation design and manufacturing processes. The A-12's development primarily influenced computational fluid dynamics, a vital tool in modern aircraft design. NASA's sophisticated computer codes, developed through A-12 testing, accurately predicted fluid flow over wings and through engines. These advancements markedly improved the understanding of aerodynamic forces and thermal loads, establishing methods that remain crucial for contemporary aircraft development. The program's wind tunnel innovations revolutionized testing procedures. The specialized facilities at NASA's Ames Research Center introduced groundbreaking techniques for separating aerodynamic and thermal effects. Presently, these testing methodologies continue supporting the development of high-performance aircraft, enabling precise predictions of flight characteristics across various speed ranges. The digital fly-by-wire system, refined through A-12 research, replaced conventional hydraulic controls with electronic interfaces. This technology transition fundamentally altered aircraft control systems, becoming standard in modern commercial and military aircraft. The system's success led to its adoption in the Space Shuttle program, demonstrating its versatility across aerospace applications. The A-12's groundbreaking achievements led to numerous technological advancements that extended beyond aviation, including the development of advanced composite materials, high-temperature fuel system technologies, specialized manufacturing processes for titanium, innovations in electronic control systems, and applications of radar-absorbing materials. The program's material science breakthroughs, formerly restricted to specialized applications, now support various industries. The techniques developed for working with titanium, which constituted 93% of the A-12 structure, established protocols for modern aerospace manufacturing. These methods ultimately transformed how manufacturers approach high-strength, lightweight materials across multiple sectors. The A-12 program demonstrated the critical importance of integrated systems engineering. The aircraft's development required simultaneous innovation in propulsion, materials, and control systems, establishing a model for managing complex aerospace projects. This approach continues influencing modern aircraft development, emphasizing the need for comprehensive solutions to engineering challenges. The program's experience with thermal management provided valuable insights for future high-speed aircraft design. The solutions developed for managing extreme temperatures, including specialized cooling systems and material treatments, established fundamental principles for supersonic aircraft development. These lessons proved particularly relevant for subsequent aerospace programs, including modern hypersonic research initiatives. The A-12's radar cross-section reduction techniques laid the groundwork for modern stealth technology. The program's innovative use of composite materials and specialized geometries influenced subsequent aircraft designs, including the Spirit and F-22 Raptor. These early stealth developments established principles that continued guiding low observable aircraft design. The program's emphasis on pilot life support systems advanced the understanding of human factors in extreme flight conditions. The solutions developed for high-altitude operation and thermal protection established standards that influence modern aerospace life support design. These innovations continue informing the development of protective systems for both military and commercial aviation applications. The A-12 OXCART's engineering legacy extends beyond specific technologies to fundamental approaches in aerospace development. The program demonstrated the value of pursuing ambitious technical goals, even when existing technologies prove inadequate. This philosophy of pushing technological boundaries, coupled with rigorous testing and validation, remains relevant for modern aerospace projects. The Lockheed A-12 OXCART remains a remarkable symbol of engineering excellence, pushing the limits of technology across various fields. From titanium alloys to groundbreaking propulsion and thermal management systems, the program's innovations in materials and manufacturing processes continue to influence modern aerospace, impacting everything from commercial aviation to space exploration. The legacy of the A-12 is not just in its technologies, but in the mindset it fostered, showing that with determination and ingenuity, seemingly impossible challenges can be overcome. What aspect of the A-12's engineering do you find most impressive? Share your thoughts in the comments below. Thank you for watching.